All right. So, Varisha, we did this yesterday, and you have any questions about laminar flow or turbulent flow, or should we go forward then?
We can go forward.
Okay. So today we will basically talk about the drag force. Okay. So before we get into the drag force, I'd like to basically talk about viscosity. Now, viscosity basically is sort of, I would say, a material's property, right? That viscosity is a property of fluid that determines the friction or frictional force acting within a fluid, right? Now, basically, it has a direct effect on the rate of flow of liquid. All right, now, so I just want to, on direct rate of flow of fluid, in fact, not liquid, just. So have you ever, or have you tried ketchup, those glass bottles with ketchup in it? Have you ever bought those?
Yeah.
So, is it easy for you to, you know, just pour the ketchup out, or sometimes, you have to hit it from the back before it starts to flow?
Absolutely not yet.
It's very easy for you to like pour it out? Really?
I'm saying it's absolutely not easy.
Yeah, okay. But if the same bottle has water, the same bottle, it just comes out natural, right? Why is
Yeah.
that really happening? Because ketchup is a more viscous liquid than water. Do you understand?
Yes.
So now viscosity has basically every particular material, right, has a coefficient of viscosity. Okay. So generally we would say that the fluid factor is called coefficient of viscosity. And coefficient of viscosity basically has the symbol of eta, which is like this, right? And generally it would be a very unique value for each material. Okay? So I just want to tell you some of the known viscosities, right? Some of them are like um, water, in fact, before we go into that, I just want to tell you something very, very important as well. So, viscosity basically is dependent on number one, density of the liquid or the fluid, and number two, the temperature of the fluid. Yeah, I'll tell you in a bit how. So, for example, like you must understand that when you look at gases, right? So gases could be air, for example, right? So for example, if I say here, look at air. So air at a temperature of 0 degrees Celsius has a viscosity of 0.000017. Okay. If you heat the air and the air temperature increases, then it is very difficult for a gas to flow at higher temperatures because the gas will be more viscous then. As you can see, I'll write here temperature, and that's viscosity. Viscosity is basically, the SI units are Pascal seconds. So air at like 100 degrees Celsius, the viscosity is 0.000022. Okay, Varisha?
Yeah.
So if you notice the trend, as the temperature is increasing, the viscosity of the air is also increasing. That makes it like at higher temperature, just shows that, right? Now if we talk about water, we talked about gases. Now if we talk about, in fact I'll write material here instead of this. So for water at 0 degrees, the viscosity is 0.0018. The same thing for water at 20, the viscosity is 0.0010. And water at 100 degrees Celsius, it's 0.0003. Do you understand this? Now, a liquid would behave very differently than a solid, a gas, right? Because as the temperature of the liquid increases, its density is going to reduce, which basically means that its flow rate is going to increase. Understood?
Yeah.
Now, let's check out chocolate, right? So chocolate is sort of a solid material when it's cold and becomes liquid really quickly. So if you look at chocolate chocolate at 30 degrees, it is basically the viscosity is 100, so it's a thicker liquid, so it's harder to flow. But the same chocolate, when you heat it up to even 50, the viscosity drops. It's like that. So what we've learned here is that in gases, as temperature increases, viscosity increases. In liquids, as temperature increases, viscosity decreases. And a lot of time he's going to ask you this, so you should be, ready for this. Okay, Marisha? If you have any questions, please let me know.
No, I'm good.
Okay. Okay. Now basically what we learned was basic just about viscosity. So ultimately we would want to go towards the drag force, because the drag force then basically relates to this. And the drag force was really introduced by Stoke's law. There was a scientist called Gabriel Stokes who has developed this equation. So he has said that Stokes' law is given by force, which is drag, is equal to 6 pi r eta and v. Okay. Now, the Stokes law, this equation does not handle complex situations. This is for only very controlled, there's certain assumptions that you need to remember. Okay. First of all, this equation is true for a small sphere moving in a fluid at low speeds. It's not about a very heavy one. Do you understand?
Yes.
Now, in this equation, r is the radius of the sphere, eta is the coefficient of viscosity, v is the velocity, okay? Velocity of sphere. So radius is in meter, this is in Pascal seconds, and this is meters per second. Okay, Varisha?
Yep.
Now imagine this could work in many situations. So usually when we would want to use it, so you can always find the drag force of a small sphere moving in a fluid at any velocity, really. But there are other factors they might also contribute to this. So let's look at those first. So suppose we got a column of, basically it's a measuring cylinder, and this measuring cylinder is filled with oil. Okay. So now you drop a small sphere that's basically moving down. So on this sphere, I just want to tell you that there will be a couple of forces. The weight of the sphere will act here. There will be upthrust that will act, and also there is going to be the drag force that is going to act. So let's write D. Is it clear? We have already done this before as well, right?
Yeah.
So in a condition where we say that it's moving downwards at terminal velocity, which basically means that at this point, let's call this Vt for now. This means that this object, all the forces are balanced. So on this object, the forces are weight, which would be the largest one, and then the upthrust. It could be, if it was moving up, that would be a different story. And the drag force. Some people like to call it the Stokes force as well, so it doesn't really matter, right? Now, so the weight of the, let's suppose we're just putting up few other variables. So let's say this is the ms, means mass of sphere, right? And rho s is the density of sphere. Okay. Let's write mf as the mass of fluid displaced, and Wf is the weight of fluid displaced. Okay, Varisha?
Okay.
And one more, rho f would be density of fluid. Now we're going to keep that in mind, these ones, before we derive the equation. And this equation, they might ask you to derive this as well, so you should be. Okay, now. So first of all, let's look at the weight. So the weight of sphere can be found out by using, because weight of sphere would be mass of sphere times acceleration due to gravity, right?
Yeah.
Then we would also want the volume of the sphere and the volume of the sphere would be given by basically volume equals to mass of sphere divided by the density of sphere. Do you agree? So if
Okay.
I want the density of sphere, sorry, mass of sphere, should I multiply, because it's a sphere, so volume would be 4 by 3 pi r cube times the density of sphere. Can I do that? What do you say? Okay. Now, let's look at the next thing. Now, according to that, then the weight of sphere can be written as 4 by 3 pi r cube rho of sphere and g. You agree? So that would be the weight of sphere, right? So basically I've replaced this right here. Okay. Now, so what I'm going to do is, in this section, I'm going to add this 4 by 3 pi r cube times rho s, and that would give me the weight. Okay, just like rho s times g. Okay, any questions now?
No, I'm good.
Okay, now let's talk about the upthrust for a moment. So, by Archimedes' principle, we know that upthrust is equal to the weight of fluid displaced. That's what we learned, right? That would mean that weight of the fluid that was displaced should be equal to the mass of fluid that was displaced times g. Understood?
Yeah.
Now, how do we find the mass of the fluid? So we got to find first through the volume of fluid displaced. Interestingly, the volume of fluid displaced would be equal to the volume of sphere itself, because whatever the volume of sphere is, that would displace equal amount of volume, right, of fluid. Understood?
Yeah.
So volume of fluid displaced would be same as 4 by 3 pi r cube, and now we can say that the mass of fluid would be equal to volume times the density of the fluid. Understood? Because density is mass over volume, right?
Yeah.
Now that helps us in getting this equation correct, because then we can write that the weight of the fluid displaced, which is equal to the upthrust, is 4 by 3 pi r cube times density of fluid. So what I'm going to do is I'm going to place it right here. And times g. You got my point?
Yeah.
Okay. So basically what I've done is I put this, oh sorry, I put this right in this equation. So you can also make the arrows so you don't forget what we've done, really. Okay. Now, now remains the drag force, and we got to write that. So we know the drag force is given by 6 pi r, the coefficient of viscosity, and because it is moving at terminal velocity, so we're going to write Vt there. Understood?
Yep.
Right. Now from this equation, we want to basically go towards, like, I would say, make terminal velocity, because we're interested in finding that, the subject. And to do that, then we got to move 4 by 3 pi r cube times density of solid sphere times g minus 4 by 3 pi r cube density of fluid times g equals to 6 pi r eta v terminal, like that. Now if you notice, there's a couple of things that we could take common. So 4 by 3 pi r cube and g, if we take common, then we get density of the sphere minus the density of the fluid equals to 6 pi r eta vt. So 4 by 3 g rho s rho f, and then we can basically divide this by 6 pi r eta, and that would give us the terminal velocity. So if you notice that the radius of the sphere is a factor, like if you take a bigger sphere, of course it's going to be like, now in fact let's just you know cancel this radius, sorry, if you cancel the radius here in the top, so it's going to be 4 by 3 pi r square g, and then rho s minus rho f over 6 pi eta. Now 4 by 3 divided by 6 is basically 2 will be like 4, 2 is 4, and 2 3 is 6, so we can further simplify it by 2 by 3 will multiply down, so 2 by 9 pi r square g rho s minus rho f Oh, let's cancel pi as well. Wait. So 2, and this will be 2 by 9 rho equals to Vt. Is it clear, Varisha?
Surprisingly, yeah.
Okay. Now, check this out. So, now we can say that the terminal velocity is given by 2 r squared g over 9 eta times rho f minus rho s minus rho f. Okay. Now, so what you really understand from this is that the terminal velocity depends on, number one, it's proportional to square of radius of sphere, number one. And then the difference of densities of sphere and the fluid it is falling in. Third, inversely proportional to coefficient of viscosity, which means if you have a greater viscosity, then of course the terminal velocity is going to be slow because the flow rate is going to be slow. Understood?
Yeah.
Okay, that's cool. So mainly in the questions, you don't really need to, learn everything here, but you got to learn this equation that helps us find the terminal velocity of a sphere falling in a certain fluid. That's what you need to know. I hope that makes sense to you, okay? Okay, Varisha, when the meeting ends, please rejoin, alright? Okay, Varisha. Now, let's do an example of this. So, in a question, it says find the velocity of number A, a steel ball of radius 1 millimeter, and B, a steel ball of radius 2 millimeters falling through glycerine. Now they say the coefficient of viscosity of glycerine at 20 degrees Celsius is 1.5 pascals seconds. Alright. Then they've given the density of steel to be 7,800 kg per meter cube, and then the density of glycerine as 1200 kg per meter cube, and you know the G is 9.81 meters per second square. Can you please do this, Varisha?
One second, please. My screen got frozen.
Okay.
Okay, it's good. is A9592. Hello? Hello?